Tell us about German surf, but
generalized symmetries. I try not to write too much because I'm not sure I will be able to erase. So that's so the title is Generalized Symmetries. I should say this work done with Nabil Iqbal, who's now in Durham. And maybe, well, I will tell you what generalized symmetries are and why I think they're very interesting. Let me tell you an alternative title for the talk, which might be how to think about gauge theories without ever saying the word gauge. So that's a bit one reason to be interested in these sort of symmetries, which are global symmetries, they're not gauge symmetries. And maybe let me say one more thing. Let me just tell you what I will not be talking about. So generalized symmetries are useful for many things. And one thing they're useful is for hydrodynamics and to understand different theories of hydrodynamics from an effective theory perspective. And one thing that we've done, for example, is we've managed to use the technology that I will explain now in the concept of hydrodynamics to derive magnetohydrodynamics just from effective field theory. And okay, there's many applications of that, but I will not be able to talk about that today. Actually, I've given this talk a few times and never get to the end, so I will certainly not get to that. If I do have time, and if you guys are interested, I might say something about holography, about how the symmetries that I will talk about in a second, how they manifest themselves in holography, and how, for example, they can connect to n=4 Spray Mills, or some examples that we know and love. Okay, that was a big preamble. But okay, so let me try to explain then what it is that I want to talk about. So I want to talk about what's called deform symmetries. So let's see. It's okay? You can read?
Mm-hmm. Yeah, that'd be good.
Okay, so deform symmetries. And what they are is a generalization of usual symmetries where the current associated to the symmetries through something like Nether's theorem, which I will come back to in a minute. It's a p+1 form. Okay? So, usual symmetries that you are familiar with are called zero-form symmetries. And associated to them, when they're continuous, there's a local one form associated to it that is conserved. For most of today, I will focus on continuous global abelian symmetries, but we can come back to other questions when you have them. So, in order for me to tell you what these guys are, let me just do as short as possible review of what the usual symmetries are, and let me put them in a language that will allow me to generalize the results. So, zero-form symmetry, as I said, is the usual one. And what happens here, what happens in this case, is that when you have a zero-form symmetry through Nether theorem, it means that there's a conserved current. Okay, so that's what it means. And a bit more grown-up language, what this means is that there's one form that satisfies this. Okay, so where that star is just a touch star. So that's one way of thinking about this. Whenever this happens, you have a conserved charge, and the reason you have a conserved charge is because you can build an operator like this by integrating star j over a codimensional 1 surface. So for today, we will be in Euclidean space, so we will do Euclidean theories. And what I have in mind is I have in mind integrating this d-1 form, right? This is a d-1 form, so I can integrate over d-1 surface. And let's think of this as a closed surface. Okay? So there will be a closed surface that I will integrate this over. Again, we might relax this and we'll talk about some asymptotic regions later on, but for now let's concentrate on closed surface. Now this is if the current J is conserved. Now this charge is a conserved charge, and the reason is that if you just take a variation of the charge, say you're trying to integrate over some region here, so this is your sigma, and then you change this, let's call this intermediate region C, So now if you make a change of the current, then what this is nothing else than the integral over the boundary of this region C. So this was the original sigma, this is the deform sigma. So this is deform sigma. And then what it means is that you have to integrate over the boundary of this region C. This thing. But then this is the same thing as doing this, which is 0. And this is why this is conserved. Now, you might, by looking at this, you might be a bit worried that you might say that you can use that to show that all charges have to be 0. That is obviously not true, so charges are not 0, they can be something else. The reason it can be something else is that we are allowed to insert things inside here that sort of break the conservation law. In which way do they break the conservation law? They break the conservation law through the word identity. So let me write down the word identity. So if we write down something like this, and we put this at some point, x, and then what we're going to do is we're going to say calculate a b, is some other operator, q, let's put it a y. I will talk about this in a second, why we're going to do that. The statement that this is, by the word identity, basically. Okay? Where this, you can think of this as a deform that integrates to 1. Okay? So, the nice thing about this word identity is that it tells you that these operators have charge q, right? Because if you just integrate both sides of this equation, you just get something like this, so integrating over x, the same thing as q. Right? So this is what is, this is a statement that these operators have charge q. Now, let's think about what we've done. So, you can think of this operator O, let me make some of this, but I have to make this a picture again. So you can think of this operator inserted here, and this is a charge that we're integrating. And see, what this is telling us already is that the operators that are charged under normal zero form symmetry, they have to be local operators. And the way they have to be local operators is because they have to be linked by the surface, right? So the charge objects, charge operators, go inside and they're surrounded by the codimension 1 surface. Okay? Here the conservation law is broken, but as long as I deform the contour around it and I don't cross any other singular points, then the charge is conserved. Okay? But the important thing that I want to point out, because I will generalize in a second, is that what this shows you is that it is local operators in the theory that are charged under normal symmetries. In terms of a Hilbert space type language, you could say that the charged states in the Hilbert space are particle states under a normal symmetry. Because you can think of this as creating some sort of particle state. So say you create something here, you need it there. And then what this surface is doing is just counting how many particles are going through the surface. So you can think of normal charges as counting particles on a Cauchy slice, right? Because it's a codimensional one, so you just grab a Cauchy slice and you just count particles. That's what this is doing.
Surface being space-like or not necessarily?
Yeah, well, it will be space-like. I'm doing everything Euclidean, but of course, in order for this Hilbert space language to be meaningful, yes, it's a space-like surface. But everything I'm going to do now is in Euclidean. Okay, so let me keep on going then. So I'll tell you maybe a couple more things that you know, and I'm sorry if this is a bit boring, let me know if I'm going too slow, and then I will generalize everything to generalize symmetries.
But I guess so far you haven't assumed Q is quantized.
No, I have not. So I have not said anything about whether the group is compact or anything, but so far it's not important. So. Very good. So now say you wanted a theory with this symmetry. So you're trying to come up with a theory that has this type of symmetry. What you would do is the following. The natural thing to do is the following. You say, well, I'll take one of these charge operators, say the one with unit charge, and I will consider that to be my fundamental field, and I will write down some action principle for it. Say, like here, that you could say is something like this, some potential, say it's a U1 symmetry, so something like this. And this sort of action will have this U1 symmetry, where phi is, again, one particular operator that you think of as your fundamental field. Well, this is a nice principal UV theory, and it has the interesting What physics is all about, to some extent, is understanding, for example, phases of theory. So I give you some UV complete theory, and then you can ask what are the different phases of that theory. So let me talk a bit about the phases of this type of theories, and then we will do everything for the higher form symmetries. So what are the phases of the theory? So the phase of the theory could be, well, the symmetry can be unbroken. And you can also call this phase a gap phase. Same thing. What this means is that if you compute the two-point function, for example, of this sort of object, it will decay exponentially. So at long distances, these correlations just decay. And then that's the statement that the system is gap, and the symmetry is unbroken in that case. So whenever the symmetry is unbroken, the charged objects are always heavy. They're always massive states. Second thing that can happen is that you have spontaneous symmetry breaking. And when that happens, these correlation functions change. Operators acquire an expectation value. Charge operators get to acquire an expectation value because the symmetry is spontaneously broken. And then as you separate these at long distances, what happens is that they saturate. At some point, the correlations decay, but at some distance they stop decaying and they just saturate. Okay, so it's very different behavior from empirical behavior. I'll say something more about this phase in a second. And maybe in parenthesis 3, you could ask about what is the phase transition actually between these two phases, and that's exactly what we call a CFT point, where the expectation value of O is 0. And then what happens is that you get power law correlation functions, which is like an intermediate situation. Now, let me just, I want to talk about the Mandelstam theorem. I will talk about the Mandelstam theorem in higher form symmetry, so let me just say a few things about that. So, see, we know that when a symmetry is spontaneously broken, there are Mandelstam modes, which are massless. And then, you know, one could say, well, what's really happening is that if I flow to the extreme IR, then I just have this massless mode, and the theory is conformal, because it's just massless modes. That's not exactly correct. The reason it's not exactly correct, I mean, it is certainly true that it's a free theory that you can think of as a conformal theory, but what's not exactly correct about that is that this theory typically comes with a scale. That will make clear in a second, it's related to stiffness. But this theory remembers some irrelevant corrections. And then when you compute correlation functions, say, of the current, they will come with this dimensionful scale. Another way of saying everything that I said, if you're a CFT person, is that these theories are free theories, and there are some way CFTs, are special kinds of CFTs where the current operators are not primaries. They're descendants. And because of that, they don't have the usual correlation functions that you know and love from CFT. So in that sense, this is different from this behavior. So now, everything I said, let me make clear. What's happening in the symmetry broken phase is that your operator phi acquires an expectation value, we call it rho, there's some phase with your Mandelstam mode. And then when that happens, you can always write the current as rho squared theta, right? So imagine a field like this and a field like that. If you just compute the current operator, it will be something like this. And this is a dimensionful coupling constant, okay? Which is parameterizing the size of irrelevant corrections to the IR field, okay? So, notice something very strange that has happened. So, what will happen, what the Mandelstam theorem says, that this field, theta, is a massless field. And the way that comes about is a bit interesting. So, see, I told you that for a symmetry to be a symmetry, this has to be true. So, that's the definition of you having a symmetry. But what happens in the symmetry broken phase is not only that d star j is 0, but d of j is also 0, right? If you just take d of this, it will also be 0. So this is another manifestation of what it means to be in a symmetry broken phase. Something quite dramatic happens, which is you get another conservation law. It's a bit of a strange conservation law because, well, if you know your forms, you will see that the dimensionality of this is a bit different. And this is a bit in connection to higher form symmetries, which I will talk about in a second. But once both of these guys are 0, then what happens is that this guy theta is just forced to satisfy the Laplace equation, basically. That means that it's a massless mode. So there's an effective action for the theory, which you can write as an action for the Mandelstam mode, which is basically this. Okay, plus the relevant corrections, right? So that's nice because this phase can be described universally by this type of actions without you knowing too much about it. Very good. So, class is over. You can now wake up. So now what I will do is I will show you how all of this generalizes to the case where the current that you start with is not a 1 form, but a P form instead. Okay? Questions about this before I do that?
So, the statement that D of J's and the other thing about 0, is that true only at leading order? It's a true also.
Yeah, that's a statement about the IR phase. There will be corrections to that. But they will be always suppressed, all those terms will always suppressed by this.
So which of these statements gets corrected?
The conservation of star J gets corrected by irrelevant terms. Of course, the actual symmetry, the one you start with. So once you have the R phase, see, it's a bit tricky, right? Because once you've gone all the way down to the IR, you have two symmetries. And if you want to go back to the UV, you could in principle decide which one is it that you want to preserve. If you stop just before you get there, there's only one of them. There's an actual one, and that's the one that's always exactly preserved. So the irrelevant terms do not affect, of course, the conservation law of the original symmetry, but they will break by irrelevant terms.
But the UV symmetry, I thought, said D of star J was 0.
Yes, so that will always be true.
Ah, sorry.
But the fact that J is D of something else will be corrected.
So the Noether current will not be just D5, it will have other terms.
That's right. Very good. So now let's generalize this to P forms. And then the statement is the following. So the statement is that now we will be concerned with objects that look like that. And then still, as before, the grown-up way of thinking about it is this one, where now this guy is a P plus 1 form. Okay, that's what it means to have a generalized symmetry. Let me emphasize, these are global symmetries. No gauge anything going on here. These are global symmetries. So what are the charges associated to them? Well, the same as before, I can integrate them over a surface. But the curious thing now is that because they're not 1 forms, star of them are not D minus 1 forms. And what that means is that these charges are not integrated over a Cauchy surface. Right? They are things that is this one, D minus 1 star J. That's the concept one. Again, these are not integrated over the full Cauchy slice, but over some subspace of the Cauchy slice. They're still conserved, and then I will not repeat the argument, but they're the same equally conserved as before for the exact same reason. You can now deform the contour, and nothing happens. But what's interesting is that now you can ask what are the charged objects under this type of symmetries, and what you will realize is that there cannot be local operators anymore. And the way to see this is to write again the word identity like this. So let's make things concrete so we don't get lost, and I can make some drawings without embarrassing myself. So let's, for a second, assume P equals 1, D equals 4. Right, so it's a conserved 2 form in a 4-dimensional symmetry. And it's a 4-dimensional series. So if you do that, then this thing is a 3 form. And say you put it next to an operator that would suggestively be called W, C. And if you look what goes on the other side, 3 form. And this is a delta function that has to integrate to 1 over a 3 form, and the only way it can do that if it's something that's localized over a contour. And it was too fast. Another way of saying that, notice that now in 4 dimensions for P equals 1, this integral is an integral over a 2 surface. Okay? And a 2 surface in 4 dimensions links a line. So let me try to make that picture. And let me try not to embarrass myself, see if I can do it. So there's something like this. This is 2 surface, and this is my line. And the line goes through the 2 surface, and the 2 surface links it. And that's what it means that I can deform it as long as I don't touch that line, and the charge will be conserved. Okay? So, what is this thing counting? This thing's counting strings. Because you can think of this operator, let me just close it here, as creating a string. So there's something that goes up, and there's something like this going on here. And then if you zoom in here, what you will see is that you're integrating over a two-dimensional surface that can close enough, it could be flat, and then it's counting how many strings are piercing it. So this new object is a conserved quantity. It's integrated over a two surface, and what it's counting is how many strings pierce it. And that thing cannot change. It's a conserved quantity.
When you say string, you're not being too specific.
I'm saying string like degree of freedom, something that's not it's not a particle.
So
it's an
extension.
extension.
Think of the one range here rather than F1.
Well, you will see in a second. So I will give you a very precise example that has all of this, and this will be magnetic flux. In general, in a non-abelian theory, you could hope to think of this as some sort of flux too.
So where did the quantization of this Q come from? You said the number of strings.
Yeah, I have not said anything about that. I have not
So
told you
what does number of strings mean then?
Sorry?
What does number of strings mean?
Well, it's just a way of saying it.
Oh, I see. Okay.
I'm just saying that the object that it counts, the operators are line operators. If the symmetry is compact, it will be quantized. I'm just counting dimensions. That's what I mean. So let me now show you where things get complicated and why our life as physicists is hard. If now I could do the exact same things I did before for these symmetries, physics would be done pretty much. And the fact that I cannot do it is why we are still fighting with interesting problems in physics. See, if you say, well, let's do the same thing as before. Let's try to come up with a theory that has the symmetry and see what happens. And then you say, well, that's very obvious what I need to do. I will grab this operator and I will write down a Lagrangian for this operator. I will just take one of these operators to be my fundamental field, and I will just path integrate over it and be done. So let's do that. You'll see in a second one. That was really bad. So let's take one of these operators. So let's call it phi of c. And look at the kind of thing that I'm forced to do at this point now. I'm a bit schematic. We can talk about betas if you're interested. So you can write something like this. This is the action. See, this gets really bad very fast, right? What this is just the action. It's not a path integral, it's the action. And the action itself is already a path integral. See, because these operators are defined on a contour. And if I want to sum over all the contours, I need to do a path integral. Right? This is a sum over all possible contours. And what I just wrote for you is string field theory. This is just one way, or actually the first type of formulation of string field theory that didn't go very far. But there's one way of thinking about the problem. These are the types of theories that have this symmetry. These derivatives in loop space can be defined, so let's not worry too much about them. It's very hard to deal with this, and this is also one way in which people try to make sense out of non-abelian theories. They try to write them in loop space, and then they realize, well, Polyakov wrote this in loop space, and he realized that the equations of motion for this type of theories are very, very, very similar for the sigma model type equations of motion. And he solved that problem first, because that was easier. And again, this brings us to where we are now. Okay? But dealing with this is very, very hard. Now, it's a bit annoying, right? Because this is what we would really like to do, but it's very, very hard to do this. So, the sort of shortcut that physics has taken is a bit, well, it's great for perturbative calculations, but makes our life miserable away from that. Well, this is a bit of a hard problem, so I will do the following. Instead of solving that problem, what I will do is I will come up with some fundamental fields that will be local human normal fields, and I will write down a theory where these objects are composites. This W field, right? They will be composites. They will not be the fundamental fields of my theory, and I will just make them out of some other stuff. And then I will have to add some constraints on top of that, so this other constituent, these fundamental fields are not really very physical, and the physical guys are just these ones. And if you just follow the word that I just said, you're stuck with gauge theory. That's how we build gauge theory. The way we do it, we come up with some other local field, and we make these guys out of the fundamental fields, and this is nothing else. I will give you in a second, but a Wilson or a Hofman in a gauge theory. So these are the typical operators that are charged as symmetries. Wilson and Hofman are typically charged as this type of symmetries. Okay? And the fact that we cannot think of them as the actual degrees of freedom is what makes life hard for us. As we know, in a strongly coupled theory like QCD, these are the fundamental degrees of freedom. These are QCD strings. It's not the gluons.
But I'm a bit confused with global and local, because...
Yeah, exactly.
Yeah, you discussed
exactly.
theories, but we were talking only global so far.
Yeah, everything I said is global. I will give you an example in a second. I'm saying that you're forced to introduce some other structure with some other artificial stuff like gauge symmetry that we would not like to talk about, and then we're forced to get rid of it, such that the fundamental fields, the fundamental degrees of freedom are those ones, and not the ones that we came up with. So this is a bit where we stuck. So I will not have much to say about this problem at this point, but just to give you a flavor of why is it that life is hard, but also to tell you, to remind ourselves that what we really want to study is not all this gauge symmetry crap. We came up with that just to fix this problem. It's completely artificial. If we want to understand the phases of this type of theories, we better go back and look at what the global symmetries are, which is, according to Landau, what we should be doing anyways. Okay?
Diego?
Yep.
So you could take QCD and write down something like Migdal-Marquinko equations and get equations for loops.
Yep.
So that seemed hard.
Yep.
Is this going to give some insight into that? I mean, why?
I don't think so. I'm not saying anything new.
Okay.
What I'm saying is, well, not new, but what I'm saying in a more modern language, and I'm focusing on the symmetries on the global. Like, Polyakov knew about all of this stuff, but I think, that, and actually the fact that the loop equations are like conservation equations for a chiral sigma model is related to the symmetries, right? So when you look at the loop equations, they look exactly like the equations from a sigma model, because there are like holomorphic and anti-holomorphic constant currents. But I guess the language is a bit modern, and I guess it's just to... I'm not being careful when it's a Blackboard talk, I have to be very careful with the citations and things like that, but this is, I guess, in the modern language, it's a paper of Cyber and France. Okay? Very good. Okay. So, let's talk a bit about the phases of these theories, and then I want to prove some theorems. Well, physicist theorems. So, there can be many phases. So, as before, there can be an unbroken phase. So, also, I will, of course, give you examples of the theories in a second. I mean, this is a bit abstract so far, but I will give you a concrete example of the theory that has all of this stuff. So, the phase can be unbroken, as before. And when that happens, because now the objects themselves are extended objects, you can phrase what's going on with the symmetries in terms of the one-point function or the two-point function. So I'll be a bit careless about that. But for example, when this happens, is that this type of operator has an area behavior. See, it's the same statement as before, that when you make the distance very large, these things are decaying exponentially, is the area low. In gauge theories. Or another way of saying it, you could say you calculate the two-point function of these guys, say, of some lines like this, say there's some distance L, some T going here, this statement that this goes with, which is like the area of that thing.
Oh, but the one-point function is 0.
Sorry?
Or you just take one straight line and say the one-point function is 0.
You could say that. Well, it's 0 because the area is infinite, right? So it's yes. So you could say that. If you consider finite Wilson lines, it's not 0, right?
I think that's the most natural analog.
I agree with that. I agree. That's a natural analog. I agree with that. Yeah. Very good. So that's the area law. The second thing that can happen is that the symmetry can be spontaneously broken, and what happens is that now this thing has a perimeter law. See, the perimeter law is the equivalent thing, well, I erase it, of the symmetry broken phase, because see, this thing, well, I called it the length, it could be a local functional, but the important thing is that this expectation value only depends on things you can compute where the operator is inserted. Right, the length of a loop, you compute by doing something iterating over the loop. The area, you cannot do that. You need to fill the loop. Right, so this is a statement that this is like the symmetry broken phase, because there what happens is at some point you separate the 2 points, the 2-point function only depends on those 2 points and not what happens in between. So it's the same, it's completely analogous to this. And then what happens is that when you separate 2 loops, that's it. The 2-point function is just given by those 2 loops and not the things that you fill inside. And as before, I will not talk about this much, but in between also you can talk about the CFT phase, where there's some gauge boson inside, and then you get a contribution that will give you the constant, say e to the minus t over L, which is basically like a constant, which is the Coulomb potential. But I think that's not talking much about that. So I want to get somewhere. So let me give you an example of a theory that has all of this behavior, so it becomes a bit less mysterious. So an example of all of this.
So just in usual gauge theory language, the first phase is confined. The second phase is what, Higgs?
Correct.
And the free Coulomb phase is going to be here.
What we're going to argue now is that Higgs is a perverse name for a phase. Okay. Because you're talking about a symmetry that you should not be talking at all.
That's fine.
So, but yeah, you're absolutely right. Yes, you're absolutely right. But it's a perverse name. Yes. Very good. So let's talk about that. So I claim that electromagnetism plus matter has all of this stuff in it. So let's talk about it. So one way to see that is like, okay, let me write down the equation of motion for E and M. So the equation of motion for E and M are like this. Okay. Where this is the electric current. I don't want to talk about the electric charge because that's the gauge symmetry. So for our purposes, the only thing you have to know is some operator here on the right-hand side of this equation. That's all I care about. There's another equation that looks like this. Now, we've seen these equations since kindergarten, and what people, perverse professors, teach us is that this equation is a bit boring because F is d of A, and this one is the interesting one that has the dynamics about Coulomb's law, whatever. And I claim that the exact opposite is true. This equation is completely boring. This equation is the definition of JE. Whatever star F is, just take d of it and give it a name. That's star of JE. Whatever, who cares? The conservation law that we typically think of in terms of JE is automatic with this definition. There's nothing to it. So this equation is completely boring. It's just a definition of an operator called JE. This one is the interesting one. Because what this one is saying is that there's a conserved quantity, that there's a two-form symmetry. Because now I can define from this some J, which is just star of F, and that guy is conserved. So this theory has one of these higher form symmetries. What is it that is conserved is magnetic flux. If you just have a surface and you count magnetic lines piercing a surface, that quantity is conserved, cannot change. You can deform the plane, you can wait in time, or you can move it up and down, and it cannot change. The magnetic flux piercing a surface is conserved. Very good. So this tells us that this theory is a theory of magnetic. If we wanted to do this very hard thing, it's a theory of magnetic tubes. Those are the string-like degrees of freedom that we should be thinking about. So this theory is non-conformal, and I'll talk more about that in a second. But we know that the theory has a running, and let's see a bit what the IR phases can be. So, unbroken. So the unbroken phase of the theory is nothing else but the superconducting phase. Whenever I give you a superconducting phase, what's really going on is that the magnetic strings, which are the fundamental degrees of freedom, become heavy. Right? So in order for you to push magnetic flux through a superconductor, you have to pay a very high price because these guys have a high tension. And when the charge degrees of freedom under a symmetry are very heavy, we say that the symmetry is unbroken. So see, it's completely the opposite type language that we are told to use, in which we're supposed to think of this as a Higgs phase for electric charge. And nothing here that's physical, that's charge and the global symmetry is condensing. Okay? Very good. What is it that that's going on? Is that what the guy, I call them W because people like Wilson loops a bit more, but what's really going on here is that the charge objects are not Wilson loops, are Toff loops. And these guys have area nodes in this phase. Okay? Very good. Of course, if you computed the Wilson line in this thing, it will go like the perimeter. And that's why you call it Higgs. Now, there's another phase, which is the symmetry broken. Can you read here still? Yes? Yeah. The symmetry broken phase. And that symmetry broken phase is the one that I will say some things about in a second. That symmetry broken phase is nothing else than a theory with massive charge degrees of freedom, electrically charged degrees of freedom. Say, take a theory of E and M coupled to 7 electrons, for example, and make the mass of the electron positive. And then what's really going on here is that you flow down to the IR, and at some point, the electron decouples. Right? So we know that E and M has a logarithmic running, but as you go down, and when you hit the electron mass, that running stops, and the theory becomes conformal. And I'll say something about that in a second. But the important thing is that this theory has a massless degree of freedom, which is a photon. I will argue in a second that that thing is the ghost-on of this symmetry broken symmetry, of this broken symmetry. Now the interesting thing is that when this happens, we know, when we're in the symmetry broken phase, we know from what I said before, is that J is not only that D star J is 0, it's also that DJ is 0. That. So this thing let me call, following this perverse language, let me call it that. So whenever we're in a symmetry broken phase, it's also true that J is D of something. Okay? And then this is nothing else but the statement that this thing decouples, and then also the electric flux is conserved. Not only the magnetic flux is conserved, but the electric flux is also conserved. There are no charges. So this is our goldstone, and these are our stiffness, in principle. And I gave them some perverse names. So let's write an effective action for the theory, which we know is a Wilson action. So same as before. Like this. And you can, if you so wish, dualize that field. And like that. And there's nothing more than ENM. Okay? This is just ENM in the magnetic variables. Okay? So the stiffness of the theory is nothing else than the gauge coupling. So if you were feeling that G had something to do with the coupling to some charges that don't exist, no, let's not say that anymore. We can now say just the stiffness related to the expectation value of some operator in the symmetry broken phase. Okay? But this points to something interesting that I will try to show in a second, which is that this IR is universal. See, you didn't have to start with ENM. ENM does not have to be a UV complete theory. ENM is emergent, and it always appears universally whenever these symmetries are spontaneously broken. It doesn't matter what the theory is, it could be a theory of dragons. But in the IR, if the symmetry is spontaneously broken, you will get ENM. And I guess I'll try to prove this now, unless there are questions.
You will be interested in quantizing the theory? Or?
Sorry?
Will you be interested in quantizing?
Well, quantizing theory is very easy.
I mean, yeah, but that's a special case where the dual is something we understand and not.
The
You
dual?
dualize the field, you dualize
Oh,
the
you can say this language. Quantizing theory is also easy. No, I just did this so I wrote this in electric parables. This theory is also easy. Let me say something about quantizing theory. So hopefully I'll convince you in a second of some results that are connected to the quantization of the theory. So let's think about what the quantum theory is for this thing. So the quantum theory here is, okay, it's a theory of this current and some charge operators. What are the charge operators? The Toff lines and the Wilson line, because both of them are charged under the two dual symmetries in the symmetry broken phase. This sounds a lot like a vertex algebra. So if you know what happens in 2D, there is no symmetry breaking. It's a lot like a vertex algebra. And I'll come back to this is exactly how it will work out, and I'll come back to it in a second. Maybe related to that, let me point something else out. There's something also funny that happened here, which is that G is dimensionless. So I told you this was supposed to be stiffness, but stiffness have dimensions typically. But in this particular case, it doesn't. And what's interesting about this thing not having a dimension, this happened in particular because I chose a two-form current in a four-dimensional theory. The same would have happened for a three-form current in a six-dimensional theory, and so on. And what's interesting about this thing being dimensionless is that this thing that typically you would have thought as a symmetry broken phase with a scale does not have a scale. Which means that the symmetry broken phase now becomes a whole conformal phase. And again, if you're a 2D enthusiast, this is very, very similar to what happens with a free boson. If I give you a free compact boson in 2D, there's a whole phase of conformal field theories parameterized by a marginal deformation, which is the radius of the boson. The radius of the boson is dimensionless in 2 dimensions, and it's a marginal deformation. The theories all look similar, but what's not the same is the content of charge operators. Right? The vertex operators are charged. The spectrum of those depends on this coupling constant, as it will be the case as well here. Very good.
Counting the goldstone, like number of degrees of freedom with the number of mass degrees of freedom.
I think it's trivial. I think it's the same. Because I have not done non-abelian cases, it doesn't get super interesting. And there's a reason I have not talked about non-abelian stuff, and let me come back to that at the end. But for abelian, it's trivial. It's the same counting as before. But I'm using but this is for a relativistic theory. If the theory was not relativistic, I think it's an interesting question. I don't think it has been studied. But understanding how this works for a non-relativistic theory, because there we know that the pattern of goldstones could be interesting in a non-relativistic theory.
Let's say if you're working in a general D-dimensional theory and you have like some P-form symmetry, when it gets broken, how many goldstones goes on to the related?
One with the right number of indices. So for a two-form current, you will get one vector degree of freedom. But again, this question is interesting in the non-lattice case for sure. So let me prove a couple of results. Hopefully I can get to say something. And it'll be a miracle if I get to talk about holography. Maybe I can say some more at the end. Other questions? Very good. So let me just now prove a version of Goldstone's theorem. And let me tell you something about these kinds of theories and universality. So I'll try to sketch a quick proof of Goldstone theorem. So I claim there's a Goldstone theorem for this. So in the symmetry broken phase, what happens is that, as we said, our operator has a perimeter law. But because the perimeter law is a local functional, what I can do is I can define the new operator, call it W bar, that is, something times the original guy, and such that I pick this guy to cancel the perimeter law. So such that this thing is 1. Okay? So you can always do that. You can always remove that. Because it's a local thing. You could not do this in the unbroken phase, right? Because this expectation value depends on the area, which is not local functioning. But in this case, you can do that. It's like removing the expectation value of a local field. And if that's true, then you can get Goldstone theorem the following in a very simple way. You just take the wall identity, Mr. J, W bar C. This also satisfies the wall identity, so you get something like this. And then what you do is you integrate this over a ball of size R. Right? So integrate this over a ball of size R. Then this thing has to be the exact same thing as the integral over the boundary of the R of star J with W bar of C.
Sorry, very super.
Yep.
You said the symmetry broken phase was the phase in which the mass of the charged particles was, all charged particles were massive.
Not charged particles, the charged strings under the global symmetry are massive. I'm not talking electric particles are not part of our problem.
Thank you.
Yeah. So I just put this D here, so I can put this as an integral over the edge. But this is morally the same thing. Say you take a sphere, for example, this goes like R squared, J evaluated R, C. Okay, I'm just doing the integral over the sphere, so it's just J evaluated over the sphere, some radius R. But the curious thing is that this is one side of the equation, this is the other side of the equation, and this side of the equation are independent. See? So this R dependence is trivial, it cancels. And what this means is that if you move the R to the other side, so the expectation value of J at some distance R from the loop goes by Q or R squared. And that's just a Goldstone. That's the statement that the massless degree of freedom. That correlational function is a power law. So it has to be a massless degree of freedom. Very good. So you can think of this as some proof of Goldstone. Very good. So I don't have infinite time, so let me try to pick something that I want to say. So what I will prove now is what we call photonization. So photonization is related to what people call bosonization in 2 dimensions, so that's where it comes from. And the statement is the following. This is what I will prove. What I will prove is that take a theory in 2D dimensions. So let me say, maybe I should say 2P dimensions. In 2P dimensions, and take a conserved P form. And a theory of that kind is such that if it's a CFT, it's always this theory. Okay? So, let me make another statement that will be very familiar, and then I will say what I just said again. Take a 2D CFT. If I give you a 2D CFT and I tell you this 2D CFT has a conserved U1 global symmetry. Okay? In principle, if you didn't know anything about CFTs, you might think that there's an infinite soup of these theories. That, they're arbitrarily complicated. But that's not true. All 2D CFTs with a U1 conserved global symmetry are such that it can be factorized and written as maybe an interesting mutual part. But all the charge degrees of freedom under the U1 in that theory can be written in terms of a vertex algebra. And that vertex, which is just the vertex operators that we typically write down into these CFTs. And all of those operators can be realized in terms of a free boson, free compact boson. So what we say is that the theory has bosonized. Any theory with a U1 conserved quantity is the theory of a free boson. There's no other choice. And this is because if J is conserved, star J is conserved, and if J and star J are both conserved, then what happens is that you get an infinite dimensional algebra. And once you get an infinite dimensional algebra, you get a free theory. That's a very quick. Now back to the statement I just made. What I claim is that the exact same thing is true in higher dimensional theories. Take a 4-dimensional theory with one of these symmetries, like a conserved 2 form. It is true that if the theory is a CFT, then it photonizes. It's nothing, it cannot be anything else but this. So it can have an interesting neutral sector, that we don't have to say anything about, but all the charge degrees of freedom under this global symmetry are given in terms of this and the Tofton-Wilson lines. That's it.
What do you mean, mutual sector?
There could be a part, you could dress, right, vertex operators with the
non-interacting with this.
Yes, that the energy momentum tensor in principle, yes. Yes, correct. And, okay, so again, I don't have too much time. So, I'm sure well, the proof of this is not hard. Let me just sketch it, and then let me say some interesting things about this. So basically, the way to prove this is the following. You start, if it's a CFT with a gel, what you do, we're in 4 dimensions. So you can now define the equivalent of holomorphic and anti-holomorphic currents. And the way you do that is you have to define a projector, P plus minus, which is basically 1 plus minus star. Okay? And then we define currents, as called which are just the projection of J over the guy. It's like mixing J with star of J. Okay? The same thing we do when we write down holomorphic and anti-holomorphic currents. And then you can compute the correlators of these guys in the CFT. But you can show that if this thing is supposed, if J is supposed to be conserved, and the theory is a CFT, then you can show that J plus is 0, and J minus is also 0. And then J plus, J minus is fixed. I will not write the function, but it's one function. That's it. That's completely fixed by the symmetries. It cannot be anything else. Okay? That's just the result. You can show using the symmetries of the theory that this is true. This is a bit different from what happens in 2D. I was already similar to 2D because in 2D what happens is that the mixed correlator vanishes and these ones do not. But the reason this changes is that self-dual and anti-self-dual forms mix in a different way in 4 and 8 dimensions than 2 and 6. So that's why this happens. So,
is this related to the fact that antisymmetric 2 tensor has a particular null state at dimension 2, say 4 dimensions?
Say that again?
If you look at conformal representations here,
yeah,
and you look at an operator that's an antisymmetric 2 tensor,
yeah,
then it obeys a unitarity bound.
yeah.
At the edge of the unitarity bound, it obeys.
Of course, that means that it's conserved. At the edge is there something, and it's this guy. Correct. But what I'm saying is more than that. Right? What I'm saying is that if you have that guy, then there has to be another one that also satisfies that. Right? Meaning that not only J is conserved, but star J is also conserved. And that comes for free if it's a CFT. It's required. Now, I didn't tell you what this function is, but this function is the exact same thing you would get if you were calculating correlators in free Maxwell theory.
Sorry, where did that statement come from? That the other one is also conserved?
Yes, good. So I have not said that yet. So this is 0, this is 0. This is the norm of something because, okay, there's some ice here that I'm sparing you because you're in Euclidean and there is some ice. So this is like the norm of something. And now you can take this star of this on both variables. And it turns out that if you do that, then this thing vanishes.
So, really sorry, but I'm missing where the input came from. What is the starting assumption?
CFT
and?
Conserved
2 form.
One of them.
But one conserved 2 form. Okay.
And if you use that and you compute these 2-point functions, you will see that these two have to be 0. There's nothing that they can be. And this one is completely fixed. Once this is true, you can take D of this equation and show that the norm of D of J plus and the norm of D star is 0. So they have to be 0 as operators. It's the exact same proof you would use in a 2D CFT. You compute Jj, it's a holomorphic function, so you take d bar of that equation, which means d bar j is 0, which means that the operator d bar j has to be 0.
Well, f if you've got an operator which has obeying d mu f mu is equal to 0, then it has to have dimension 2 by unitarity. Right?
Correct.
Therefore, star f also has to have dimension 2.
That's correct.
And therefore, it has to obey these
That's correct.
finite.
That's correct.
By unitarity, basically.
That's correct. Very good. So, okay. So, let me tell you what I will not tell you. So, again, let me emphasize this again. This function is the exact same function you would get if you were to calculate this correlator in free Maxwell theory. So this is a statement that all the correlators in the theory, if you put this argument, can be computed by Maxwell theory. That's a statement of photonization. Furthermore, well, okay, so that's one statement. Also, because this theory is just a free theory, it has an infinite dimensional algebra. And it turns out that you can just build that infinite dimensional algebra. There's a Kac-Moody algebra that arises for all of these theories. If it's a CFT, it has to have a Kac-Moody algebra. And this is, I will write now what the charges are, but I will not tell you that's very interesting. If I had more time, I will tell you about that. There's a formalism in which you can rewrite all of this in a very formal but interesting way, which is that what's really going on, see, well, let me write some equations and then I'll show you exactly what's going on. So let me write this chart. So I claim that this is a constant quantity, integrate over sigma 3, so take J plus, for example. And this is conserved provided pi plus j. Sorry, lambda. So let me say what I mean here. So this is a 2 form. This is a 1 form. The statement is: give me a 1 form that satisfies some condition I will tell you about in a minute. And for every 1 form that you give me, I can construct a conserved quantity. The condition it has to satisfy is that the self-dual component of its exterior derivative vanishes. Okay?
So you dot this 1 form, will you?
Sorry? Say it again. This is a 1 form. Take d of that, and then you project onto self-dual or an anti-self-dual space, and that thing has to be 0. So now let me put this in familiar language. This is very, very similar to saying that in a 2D CFT, you give me a function, a holomorphic function, which means that the self-dual part of d of that is 0, right? It has no d bar part. And then for each function like that, I can give you a conserved quantity. The same thing is true here. Notice, well, okay, there's another equivalent one for the other side. Let's write this in another equivalent one. J minus and the plus. And then the statement that these guys satisfy Kac-Moody algebra. The mixed commutator satisfies Kac-Moody algebra. I will write in a second. But notice something very interesting. These charges, even though I started with these higher form symmetries, these charges are not of this funky kind. They are normal human charges. They're integrated over Cauchy slices. So even though the theory had a higher form symmetry, in this case, when the theory is a CFT, what happens is that you can build normal human Kac-Moody charges over a whole Cauchy slice.
So these are the Noether charges for what? Gate symmetries, and in the case of electromagnetism, what?
No.
What are they?
These are global.
So in the case of electromagnetism, what would it work out to be?
These are different moments of the magnetic flux. Integrated. You integrate the magnetic flux over a surface, but then you weight in volume. You extend the charge over volume, so you would be integrating over a plane, but now you sum over many different planes with some weight. And all of these guys are conserved.
And these are not Noether charges for some symmetry for.
Now I'll tell you what they're related to in a second. If you have a so these are compact slices in principle. So let me now extend it to infinity, and I'll tell you what they're related to. But okay, but these guys satisfy Kac-Moody algebra. So I will not show it, but basically Q bar satisfies something like an integral over sigma 3 of lambda d lambda bar, which is is like a Chern-Simons term. Maybe like a mixed Chern-Simons term. And this is the generalization of what happens with the Cauchy-Moody algebra in 2D. So let me say a couple of things about some interesting formalism, and then I'll tell you what these guys are connected to that you might know about. So, what is it that's hard about these charges? What's hard about these charges is that solving this constraint is very hard. Coming up with a complete space of one forms, such that D of them is self-dual or anti-self-dual, is a hard equation to solve. It's very, very different from the holomorphic condition, which is very easy to solve. It's holomorphic or anti-holomorphic function. The reason this is happening is the following. See, in 2D, complex analysis helped us in some way. So we would like to find complex analysis here, right, to do the same thing. But what's the problem? What the problem is that in 4D, the space that has a natural definition with a complex structure is not the physical space, but it's really twistor space. It's a coincidence that in 2D, twistor space is just coordinates, just C and Z bar. That's twistor space in 2D. It's just a coincidence that these two spaces coincide. In 4D, they do not coincide. So associated to this space, you can build twistor space on top of it. It's CP3 for dimensions. And it turns out that this condition is very easy to solve in terms of this Penrose transform. That's not unrelated to this X-ray transform that we heard. And the statement is that what really happens is that these things and these currents are defined over light rays. It's not over the space, physical space, but they're defined over light rays. Everything I'm saying is completely incomprehensible to no one, to people that don't know about twistors, and it's completely trivial to people that know about twistors, and I cannot fix this in 2 minutes. But the statement is that if you go to twistor space, all the formalism of 2D CFTs goes completely, you can just translate it exactly to 4D. And all correlators and all commutators can be computed by contour integrals, by just picking up poles, the same way you do it in 2D CFTs. So there exists a formalism that puts the theory in complete equivalence to 2D CFTs.
This condition that you wrote down, isn't it just the instant on condition?
Yeah, exactly. And that's why twistors appear, because twistors also appear to solve this self-dual instant on conditions. Correct.
So, I'm just trying to understand these so
yes, I'll tell you in a second what they're connected to. Yes, go ahead.
But suppose I take epsilon mu alpha beta, f alpha beta,
yes.
del mu theta first. So
Yep.
theta is a function. This is a concept.
Oh, so it's not this one. So it's not satisfying this.
Okay. But that's another conserved character, right?
Yes, but it's boring because it's 0.
Okay.
So yeah, so you can ask me why do I demand this? I could when I need okay, let's see why this one's conserved, right? So this one's conserved, right? Because D, let's take D of this, right? So we know the first one is 0 because both J and J bar are conserved, so D of J is 0. So this is just like J D of lambda. So one stupid thing you could do is say, well, let's just demand that D of lambda equals 0.
Right.
But if you do that, then this thing is zero, because this thing integrated over a compact surface. If this is true, then this is D of something, and then I can integrate to a boundary term, and then you get 0 over a compact surface. So that's why I cannot do this, because if I do that, then it's boring.
Okay.
So I need to have something such that this is 0, and this is not 0.
Okay.
And then that's a condition. That's exactly that condition, right? This thing is in self-dual, this one's anti-self-dual, so they cancel and they don't. And the wedge gives you 0. So that's exactly that condition.
So you're using both.
Yes.
So I think you can wrap up.
Yes, I'll finish in 5. So let me just say one thing and then I'll stop. So, sadly I could not tell you about holography. If you are interested in how the things are realized in holography, n equals 4 super-Yang-Mills has the symmetry, and how this is realized in holography is very much related to what the gauge group of n equals 4 is. So in holography, we don't say too much about whether the gauge group is UN, SUN, or SUN mod ZN. And the difference between those things, it has to do with the realization of the higher form symmetries. This is a one-liner, if you want to know more, ask me. But it turns out that there's a way we can do holography for that. You can just write down the Lagrangian for type 2B supergravity, and depending on boundary conditions on the fields, you will get either U1, SUN, or SUN mod ZN, and then the symmetries will be realized differently. If you have questions, ask. The last thing I'll say, maybe it's just to appease curiosity, is that, say for a second, the theory was not a CFT. Okay? So if it's not a CFT, I cannot do this because I don't have two conserved currents. But I can always do this. And I say 1J is conserved. I can do this, which is what Curiosity was suggesting. So you can always do that, because this one is conserved always, even if it's not a CFT. And I just put something like this, and then it will always be 0. I just argued a second ago that this is boring. It's just 0. But that's true if this is a compact surface. If this surface is non-compact and goes to infinity, there could be an interesting boundary term. And the charge does not have to be 0. When that happens, these guys just coincide to the charges that are associated to the soft photon theories. So all of the discussion about soft photon theories in terms of asymptotic symmetries and large gauge transformation, blah, 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 you can forget about all of that language and you can phrase it in terms of global symmetry. And it's just these charges. And those are the ones associated with all the world identities that come for the soft photon theorem. And as you can notice, these are always present, even if the theory is not a CFT. Even if the theory has massive degrees of freedom, this will still be true and they will have some constraint asymptotic. So I need to wrap up, so let me just finish. I didn't tell you about holography, so if you have questions, you can ask me. I didn't tell you about hydrodynamics. If you have questions, ask me. And maybe I didn't emphasize it, but maybe you can think of this as a non-perturbative proof of the end of this logarithmic running, right? The statement is, so maybe what you can think of is the following. We know from perturbative QED that if you have charged matter, say massless or low mass, if your energy is higher than the mass, we know that those theories cannot be conformal. There's a logarithmic running. There's a lambda pole. So we know that. You can take my results to mean to be a non-perturbative proof of them. Whenever the theory has it's in the unbroken phase, it cannot be conformal. If the theory has massive electric degrees of freedom, then it cannot be in the. If you're not in the conformal phase, then if you're in the conformal phase, you're forced to have both symmetries. So whenever the electric symmetry is broken, you cannot have a CFT. Right? Let me say it one more time. If you have a CFT, you have to have both electric and magnetic symmetries. So if you only have magnetic symmetries, because there are electric charges in the game, then it cannot be a CFT. So this is a non-perturbative proof that it cannot have electric charges and make a CFT. It will always. Okay, let me finish here. And if you have questions, we can provide it over later. Thanks.
Can still take a couple of quick questions.
Last thing that you were saying, this doesn't require all this symmetry. This follows from conformal symmetry alone, right?
What?
The fact that you can't have charged particles with a given case theory which is conformal.
I just showed that. That's what I proved.
Right, but this just follows from conformal symmetry.
Well,
if you have f which is 0, then f equals d is 0.
Sorry?
That you have some two-form thing, f mu, which has d is equal to 0, then its conformality tells that the star f is also that thing, and then that also has 0. So which means that there are no electric, no magnetic charges. And so basically the theory is free. There is no charge particle. But anyway.
Okay, I'm not sure I answered the comment.
So this may be a bit naive, but could you use these generalized global symmetries to run through a Coleman-Mandula type argument?
Well, these soft photon charges are an example of that to some extent, right? They're some sort of breaking of the Coleman type argument. Now, in general, it's a bit hard, right? Because this, I don't know how to think about the S matrix of the theories. I guess whenever they're free in the IR is more clear, I think. But if that's not true, I don't know what to say, right? Because the degrees of freedom are string-like. And thinking about the S matrix, I don't know what the rules of the game are for that. I mean, in string theory we do that. It takes some technology, and I'm not sure how to say something more general. Whenever we're in this situation, I think it's fine, right? When the IR is free, then I think it's fine. And then that's an example of a breaking, right? The soft photon charges are an example of that to some extent.
But you didn't say anything about the non-abelian.
Yes, why didn't I say something about
which would be...
Yes, why didn't I say that? So, let me just say a fact, and then maybe try to... yes. This reminds me. Next time a student asks you, why is the photon massless? Don't say it's the gauge symmetry. It's a terrible reason. We invented that symmetry, so it cannot be because of that. The photon is massless because there's a global symmetry spontaneously broken, which is this one. So back to, now that I said this, let's go back to non-abelian stuff. So the reason this non-abelian stuff does not work is a bit annoying. It's because these charges, not these ones, the naive height form charges, they're not defined on Cauchy slices, right? So they're defined on subspace of Cauchy slices. And the problem with them is that they don't come ordered in time, right? So if you have two subspaces, they can shift them around, they can go through each other. So you cannot define a non-trivial commutator, and then you cannot have non-abelian stuff. So this is an argument in Cyber's paper that you cannot have this. It's hard to non-abelianize this.
Just more naively, in a non-abelian gauge theory, F theory was not an operator.
That's
It's not a gauge theory.
That's right. That's right.
That's
That's another way. But non-abelian gauge symmetries do have continuous and discrete versions of the higher form symmetry. So they have Z. Whereas an SUN theory has Z and generalized global symmetry, for example. Okay. So that's one story about the non-abelian stuff. Now, there are two more things that are connected to this. So, one thing you might think that one reason it's hard is the non-abelian theories don't want to be free in the IR, and it's the same thing. So it's another manifestation of this, that they don't want to have this symmetry broken phase, and so that's why it's hard to explain it like that. On the other hand, if you write down that monster of string type Lagrangian that I wrote, it's very easy to write down something that has a non-abelian structure. This loop space thing that no one knows what to do with, it's very easy to write down something like that that has a non-abelian structure. How that realizes itself, because we don't know what Nether theorem is in this case. So how does that appears in the low energy local effective Lagrangian? I don't know. Now, having said all of this, let me say two more things. One is that the higher form non-abelian stuff cannot give me interesting charges. Notice that maybe these ones are okay, right? Because these ones now are over Cauchy slices. So maybe I cannot, maybe what happens when the theory is non-abelian, that there's some sort of covariantly conserved current that I cannot use to build a higher form charge, but that I can use through these tricks to build normal charges. And maybe that's what's going on in non-abelian symmetry. I don't know what. That's one thing. And then the last thing I'll say is that very different from non-abelian gauge theories, gravitons want to always be massless in the IR, right? The theory does not want to confine. It always wants to have a massless degree of freedom. So it's very tempting to say that the graviton is also a ghost. But then you have to understand a bit more what's going on with the symmetries. There's some non-abelian stuff going on there, but there's also some abelian stuff, right? Because there are translations. So maybe there's a way of saying this for the graviton. Okay, I don't know how to say it, but it seems to some extent that it's easier to say for the graviton than for non-abelian gauge theories, because the IR phase wants to be spontaneously broken.
So you seem to use 4 dimensions very.
That's an example. So this thing does not rely on that. Let's do this in any dimension.
This projector relies on that.
Yes, correct. So the statement that photonization relies on that. So it's even dimension. So in any even dimension, a form that's half rank, that's conserved, implies this. So in 6D,
it won't be Maxwell theory.
Well, it's a theory for a two-form gauge field, and the same thing applies.
Okay, I think maybe we're ready to break for dinner, so let's thank Diego again.